Hello everyone. In this video we'll be trying out a few more problems around the normal distribution. Nothing dramatically new here compared to last class, mostly just practice and application. So in this question, the men's finishing times for a 10-kilometer race were normally distributed with a mean of 41.3 minutes and a standard deviation of 3.2 minutes. Johnny ran the race in 39.2 minutes and Mark ran the race in 43.1 minutes. If 3,000 men ran the race, we need to determine a few things. First, we need to determine the number of men between Johnny's time and Mark's time. So we can do this a couple ways. We could use normal CDF in our graphing calculator, or we can convert these times into z-scores and use Desmos. But we'll maybe try Desmos first. So the z-score of Johnny is going to be given by x minus mu over sigma. Because Johnny ran the race in 39.2 minutes, that's x. The mean is given here, it's 41.3. And the standard deviation is given here, it's 3.2. So we are going to subtract 41.3 and divide this whole thing by 3.2. And that gives us a z-score of negative 0.65625. And now we need to do the same for Mark. Because Mark ran the race in 43.1 minutes, that'll be x. So the z-score for Mark will be 43.1 minus the mean, which is 41.3. And divide that by the standard deviation of 3.2. This gives us a z-score of 0.5625. So this we need to adjust our lower boundary to negative 0.65625 and our upper boundary to 0.5625. We can try sliding these around by hand, but it's probably quicker just to open up this side tab and enter our lower boundary here and our upper boundary here. So we can see the race times we're interested under the curve, and 45.73% of race times fall between Johnny and Mark. So now we need to multiply that percentage as a decimal, which is 0.4572, by the total number of men in the race, which is 3,000. And that gives us a result of 1,372. Doing this in our calculator is a little bit quicker. We go second vars, normal CDF, we enter our lower boundary, which is 39.2, and then we enter our upper boundary, which is 43.1, and then we enter the mean, which is 41.3, and the standard deviation, which is 3.2. We go enter on paste, enter again, and you see 45.7%, which is consistent with our result in Desmos, but it was nice that we didn't have to calculate z-scores. So next we're going to figure out how many men had less than Johnny's time. Johnny had a time of 39.2, so we basically need to figure out what this area would be. So in our calculator we pull up normal CDF again. Oh, shoot. I pulled up normal PDF. So what I'm going to do is pick normal CDF, which I meant to do, and oh, that looks weird. So if we're going to proceed with this, we should probably just quit and restart. So we're going to go second vars and pick the correct thing this time. Our lower boundary is as far left as we can get, which is that number, negative 1 times 10 to the 99. Our upper boundary is 39.2. The mean is 41.3. And the standard deviation is 3.2. So we got 0.2558 and so on, which would be about 25.6%. So with that number, we can figure out how many had less than Johnny's time. We go 0.2558 and multiply that by 3,000, which gives us a result of 767. Next, we need to determine the number of runners that got more than Johnny's time. So there's a couple ways we can do this. Knowing that Johnny lives around here, we determined that 25.58% of runners did better. So if we subtract this number from 100, that would give us the number that did more than Johnny's time. So if we go 100 minus 25.58, that gives us 74.42%. Alternatively, we can do normal CDF again from scratch. So we go second vars, normal CDF. This time our lower boundary is 39.2, and our upper boundary is as far right as we can get. Our mean and standard deviation stay the same. We hit enter on paste and enter again, and we get the same result. So either way, what we do with this 0.7442 number is we multiply it by 3,000 and that gives us the number of runners that got a time higher than Johnny's. So this turns out to be 2,233. Next, we need to determine the number of runners that got less than Mark's time. Mark's time was 43.1, which was higher than the mean, so we need to figure out what this area is. Again, we can do normal CDF, so we go second vars, normal CDF. This time our lower boundary is as far left as we can get, so we go -1 times 10 to the 99. Our upper boundary is 43.1. The mean and standard deviation stay the same, and we get 71.3%. So this lower area is 71.3%, and we can determine the number of runners that represents by multiplying the percentage as a decimal by 3,000, which gives us 2,139. I'll leave these next two for you to try out on your own, and let you confirm that part E represents 861 runners, and part F represents 2,946 runners. So in general, if a data set is normally distributed with a mean mu and a standard deviation sigma, then the normal CDF function calculates the area under the curve between the lower and upper bound by following the sequence of buttons on your calculator. And if there is no lower bound, then you use -10 to the 99, which is close enough to -infinity for us here. And if there is no upper bound, we use 10 to the 99, which is again close to +infinity for us for this situation, because the outer edges of the normal distribution contribute very little. So on to number 2. A supermarket has determined that the average wait time at an express counter is 200 seconds, with a standard deviation of 40 seconds. Assuming a normal distribution, determine the percent of customers that will wait longer than 3 minutes. So to answer this question, we can use normal CDF, put in our lower bound of 3, put in our upper bound of 1 times 10 to the 99. The average is given here, 200 seconds, and the mean is given here, which is 40 seconds. So do you notice anything wrong about what I've just written? If not, now might be a good time to pause the video and see what I missed. So it looks like I should have written something other than a 3 here, because what the calculator is being told to do here is to figure out how many people have to wait longer than 3 seconds. And that's probably going to end up being most people. So rather than putting a 3 here, we need to put the equivalent in seconds. So we can multiply 3 by 60 seconds, because there's 60 seconds in a minute, and we get 180. So we can type that into our calculator. We go second vars, normal CDF, enter. The lower bound is 180. The upper bound is 1 times 10 to the 99. The mean is 200, and the standard deviation is 40. So it looks like 69.1% of people have to wait longer than 3 minutes. So let's write that down, 69.1%. So this next one is going to be for you to do. So if you wish to use Desmos, you can either calculate z-scores first and change the lower and upper boundaries as is, or you could also choose to open it up and modify the mean and standard deviation on the left-hand side. But it'll probably end up being quicker if you just pull out your calculator and use the normal CDF function. Just don't forget to multiply your percentages as a decimal by 3200. And I'll leave it to you to confirm that this is 647 and this is 1779. I'll leave number 4 for you to do on your own as well. Just note that any mixers that last between 7 and 10 years need to be replaced. So we'll do question 5 together. A car manufacturer has determined that engines in the Python car have a mean life of 80,000 kilometers with a standard deviation of 10,000 kilometers. For how many kilometers should they guarantee the engine if they do not want to replace more than 2% of them? So let's start by writing what we know for sure. We know the mean is 80,000, and we know the standard deviation is 10,000. In this question, we want to find a sliver under the normal distribution where the upper bound makes it so this area is 2%. And because our calculator is expecting inputs as a decimal, we express 2% as 0.02. So to solve this question with our graphing calculator, we're going to have to use the inverse normal function. The area we're after is 0.02, the mean is 80,000, and the standard deviation is 10,000. So we hit enter a bunch of times, and we find out our upper boundary should be 59,462.5. So let's record what we did. We did INV norm with 0.02, 80,000 was the mean, and 10,000 was the standard deviation. And again, this gave us 59,462.5. So it would be nice to pick a good round number in this case, because consumers might be a little bit wary of such a specific number. They might be reluctant to buy a car from a manufacturer that was so cold and calculating. So if this is a company that's really after their bottom line, they might be conservative and call it a 500,000 kilometer guarantee. Or if they were feeling a little bit more generous, they could do 600,000, which isn't really that much more generous, but that would probably be the better choice in this scenario. So let's go with 600,000 kilometers. So if we were to confirm this answer with Desmos, we would need to turn this number into a z-score. So we would go z equals x minus mu over sigma. X is 59,462.5, mu is 80,000, and sigma is 10,000, which gives us a z-score of negative 2.0537. And if we drag the lower limit as far left as we can go, and switch the upper limit so that it's negative 2.0537, as it is here, you can see the percentage that this represents is 2%. Which is exactly what we needed. So we'll do question number 6 next. A lawnmower company knows that the average life of lower mowers is 9.3 years, and the standard deviation is 2.2 years. The company does not want to replace more than 6 out of the 200 lawnmowers it expects to sell. What guarantee to the nearest tenth of a year should the company provide in order to satisfy its replacement policy? So let's start by writing what we know. We know the mean is 9.3. We know the standard deviation is 2.2, and we can determine the replacement percentage as a decimal by going 6 over 200, which gives us 0.03. Now if we want to determine our guarantee, we do inverse normal. 0.03 is our area, 9.3 is our mean, and 2.2 is our standard deviation. So you can try this out yourself, and you'll see that it's 5.16. So the guarantee should be 5.2 years. And we can confirm our answer in Desmos by changing this to a z-score. So we go z equals x minus mu over sigma. X is 5.16, mu is 9.3, and sigma is 2.2, which gives us a z-score of negative 1.88 and some other digits. So if we want to check this in Desmos, our lower limit should go as far left as we can, and our upper limit should be at negative 1.88. And you can see this sliver of area represents 3%. So I'm going to leave this last question for you to do. Just remember, this function in your calculator always works from the left. So knowing that the entire area under this curve represents 100%, and we want this portion to be 33%, the percentage on this side of this boundary should be the complement of 33%. So that's it for me for today. I'll see you next time.